Hello and welcome to Space Historians. I'm glad you've joined me tonight, ready to slow down, breathe deeply, and let your thoughts drift weightlessly beyond our world. This is your moment to leave the noise of the day behind and step quietly into the vast, star-lit corridors of cosmic history. Each episode here isn't just about stars. It's about the stories they hold, the quiet mysteries still waiting in the dark, and the gentle questions that help us rest. If you enjoy these quiet journeys, a like and a subscribe help keep this channel orbiting. But for now, you don't need to do anything but listen. Picture a future so distant it almost slips beyond what the human mind can comfortably hold. Not tomorrow, not next week, not even in billions of years, but in a time so far ahead that numbers lose their meaning. In that future, the universe will not end in fire. It will not collapse in violence. It will not tear itself apart. Instead, it will fade into something almost unimaginable, perfect stillness. Every star that ever shone will be dark. Every galaxy that ever glowed will be silent. Every black hole that ever bent space-time will have evaporated into nothing. What remains will not be empty, exactly, but it will be close. A thin wash of radiation spreads so evenly across space that nothing can happen anymore. No light, no heat, no motion, no change. Just silence. This is called heat death. The phrase itself sounds dramatic, as if the cosmos might burn out in a final blaze, but the truth is quieter. Heat death is not about flames or explosions. It is about balance. It is about energy spreading so thin, so evenly, that the universe loses its ability to do anything at all. No stars can shine because there is no fuel left to burn. No galaxies can collide because they have drifted too far apart. No life can exist because there are no gradients of energy to sustain it. It is the end not of existence, but of events. The universe will still be there, stretched across unimaginable distances, but nothing within it will move, nothing will change. It will have reached a state physicists call maximum entropy, where everything is uniform, balanced, and inert. The idea feels impossible at first. Right now, the universe is alive with activity. Stars blaze in the night sky. Galaxies swirl with billions of suns. Planets orbit, moons tug at oceans, and life flourishes on at least one small world. The cosmos is full of contrasts, hot against cold, light against dark, matter against emptiness. It is hard to imagine all of that fading into evenness, yet the laws of physics point in only one direction. Energy cannot be created or destroyed, but it can spread, and once it spreads too far, it becomes useless. A campfire burns brightly because fuel is concentrated in one place, releasing heat and light as it transforms. But when the fire dies, the warmth dissipates into the air, the smoke drifts away, and the ashes cool. The energy is still there, but it is no longer doing anything. The universe, in the end, is like that campfire. This vision of heat death is not new. Scientists have been imagining it for over a century, ever since they understood the second law of thermodynamics. That law says that in a closed system, entropy always increases. Entropy is often described as disorder, but it is more accurate to think of it as evenness. Things spread out, differences fade, patterns dissolve, and the universe, as far as we know, is the ultimate closed system. There is nothing outside it to add fresh energy. Once the gradients are gone, they are gone forever. What makes this idea so striking is not just its scale, but its patience. Heat death does not arrive suddenly. It unfolds over time, spans so vast they defy comprehension. The universe is already nearly 14 billion years old, but that is nothing compared to what lies ahead. Stars will continue to burn for trillions of years. Black holes will linger for spans measured in numbers, with 100 zeros. The The universe is not rushing toward its end. It is strolling, slowly, inevitably, towards stillness. And yet, even now, the process is underway. Every star that burns is using up fuel it will never get back. Every galaxy that shines is radiating energy into the void. Every black hole that forms is locking mass away, only to release it later as faint radiation. The universe is already fading, already spreading its energy thinner and thinner. We live in the middle of the story, in the age when stars still shine and galaxies still glow. But the ending is already written. Heat death is not a hypothesis among many. It is the most likely fate of the cosmos, supported by every observation we have. The expansion of space, the cooling of the cosmic background, the exhaustion of stars, the evaporation of black holes. All of it points in the same direction. The universe is heading toward equilibrium, and equilibrium means silence. To imagine this future is to confront something both terrifying and strangely peaceful. Terrifying because it suggests that everything we know, everything we love, everything we build, will one day dissolve into uniformity. Peaceful because it shows that the cosmos does not end in chaos, but in rest. The universe will not fight its ending. It will simply exhale, slowly, over eons, until there is nothing left to release. And so, as you settle into this story, let yourself drift with the scale of it. The stars above you, billions of light years away, are part of the same journey. The warmth in your blanket, the hum of your body, all trace their origins to energy released long ago when the universe was young and hot. That same energy, still moving, still spreading, will one day fade into evenness. From a blazing beginning to a whispering end, it is the same thread. Tonight, we follow that thread. We trace the slow journey from a cosmos of light to a cosmos of stillness. We walk through the ages of stars, the silence of remnants, the evaporation of black holes, and the final rest of everything. This is the story of heat death, the impossible stillness that waits at the end of time. Before we step into the far future, it helps to pause and look around. Where are we now, in this moment, in the grand sweep of cosmic history? The answer is both humbling and extraordinary. We are alive in what physicists call the stelliferous era, the age of stars. It is a time of brilliance, structure, and possibility. A time when the universe is still young enough to be full of light. Right now, the cosmos is approximately 13.8 billion years old. That sounds ancient, and in human terms, it is. Civilizations rise and fall in mere thousands of years. Your life spans only decades. Even the oldest trees on Earth have lived for only a few thousand years. But on the scale of the universe, 13.8 billion years is early. The stars are still burning. The galaxies are still forming. The story is just beginning. Look up at the night sky on a clear evening, and you see the evidence all around you. Stars scattered across the darkness, some faint, some bright, each one a nuclear furnace, fusing hydrogen into helium, releasing light and heat into the void. If you are far from city lights, you might see the Milky Way, a soft band of glow stretching from horizon to horizon. That glow is the combined light of billions of stars, all part of the galaxy we call home. Our sun is one of those stars. It sits about halfway out from the center of the Milky Way, orbiting slowly in a spiral arm filled with dust and gas. It is not the largest star, not the brightest, but it is steady. It has been shining for about 4.5 billion years, and it will continue to shine for another 5 billion or so before it exhausts its fuel and begins to die. For now, it pours energy into the solar system, warming Earth, driving weather, and sustaining life. Earth itself is a small planet, the third from the Sun, with oceans, continents, and an atmosphere that makes it unique in the solar system. Life has flourished here for billions of years, evolving from simple cells into forests, oceans full of creatures, and minds capable of wondering about the cosmos itself. That wondering is part of the setting too. Humanity is not separate from the universe. We are made of it, built from atoms, forged in the hearts of ancient stars. This moment, right now, is part of a larger pattern. The universe began in a state of incredible heat and density, a blaze of energy we call the Big Bang. As space expanded, it cooled. Particles formed. Atoms came together. Gravity pulled matter into clumps, and those clumps became stars. Stars gathered into galaxies. Galaxies clustered together. Over billions of years, the cosmos transformed from a simple, featureless fog into a rich tapestry of structure. We live in the middle of that tapestry. The early universe was too hot, too chaotic, too simple to support life. The far future will be too cold, too empty, too still. But here, in this narrow window of time, the conditions are just right. Stars shine steadily. Planets orbit in stable systems. Chemistry allows for complexity. Life can arise, think, and wonder. The setting is not static. Even now, the universe is changing. Space itself is expanding, carrying galaxies away from one another. The farther a galaxy is from us, the faster it recedes, stretched by the growth of space itself. This expansion was discovered nearly a century ago, and it revealed something profound. The universe has a history. It is not eternal in its current form. It had a beginning, and it is heading somewhere. Where it is heading is the subject of this story. But for now, the setting is vibrant. The Milky Way contains hundreds of billions of stars. Beyond it, there are hundreds of billions of galaxies, each with their own stars, their own planets, their own histories. The night sky is crowded with light, even if much of it is invisible to the naked eye. Radio waves, infrared light, X-rays, all of it pours through space, carrying information about distant suns and ancient explosions. Closer to home, the solar system is a tiny neighborhood within the galaxy. The sun anchors it, with 8 planets orbiting in ellipses. Rocky worlds like Earth sit near the sun. Gas giants like Jupiter and Saturn orbit farther out. Beyond them, the icy reaches of the outer solar system stretch into darkness. Comets drift. Asteroids tumble. Moons circle their planets. It is a system in motion, held together by gravity, shaped by billions of years of collisions and migrations. On Earth, life goes on. Trees grow, rivers flow, animals move across the land, humans build cities, tell stories, and look up at the stars. This too is part of the setting. Life is rare, perhaps extraordinarily rare, but it exists. It is powered by the sun, which is powered by fusion, which is powered by gravity, which is powered by the laws of physics that have governed the universe since the beginning. The setting is temporary. That is important to understand. The stars will not shine forever. The galaxies will not always glow. The solar system will one day dissolve. Earth will be consumed when the sun swells into a red giant. But that is still billions of years away. For now, the setting is stable, rich, and full of possibility. This is where we are. A small planet orbiting a middle-aged star, halfway out in a spiral galaxy, in a universe that is still young by cosmic standards. Around us, the night sky blazes with the light of countless suns. Beneath us, the ground holds the remnants of ancient stars, their atoms now part of oceans, mountains, and living things. Above us, the story of the cosmos continues to unfold, slowly, patiently, heading toward an end we cannot see but can imagine. So as we step forward into the future, into the long arc that leads to heat death, remember where we started. We are here, now, in the age of stars. The campfires are still burning. The galaxies are still bright. The universe is alive with energy and structure. This is the setting, the luminous middle of a story that began in fire and will end in silence. The idea of heat death rests on one of the most fundamental principles in all of physics. It is not a speculation or a guess. It is a law discovered through careful observation and tested across countless experiments. It is called the second law of thermodynamics, and it says something simple but profound. In a closed system, entropy always increases. The discovery of this law did not happen all at once. It emerged slowly over the 19th century as scientists studied heat, energy, and motion. Engineers were building steam engines, trying to understand how to extract work from burning fuel. Physicists were measuring how heat flowed from hot objects to cold ones. Chemists were watching reactions unfold and noticing patterns. All of these observations pointed to the same underlying truth. Energy spreads, differences fade, systems move toward balance. One of the first to recognize this was a French engineer named Sadi Carnot. In the 1820s, he studied the efficiency of engines and realized that no engine could convert all its fuel into useful work. Some energy always escaped as waste heat, spreading into the surroundings. This was not a flaw in design. It was a fundamental limit. The heat could not be gathered back up once it dispersed. The process was irreversible. Later, scientists like Rudolf Clausius and William Thomson, who later became Lord Kelvin, formalized these ideas into the second law. Clausius introduced the concept of entropy, a measure of how spread out energy is within a system. He showed that in any process, entropy either stays the same or increases. It never decreases on its own. This was the key insight. The universe has a direction. It moves from concentrated energy to dispersed energy, from order to evenness. To picture this, imagine pouring cream into coffee. At first, there are swirls, patterns, little currents of difference. The coffee is dark, the cream is light, and the boundary between them is clear. But if you wait, the swirls blur. The cream and coffee mix together until the cup is one uniform shade of brown. The system has reached equilibrium. The entropy has increased. You could stir the coffee all day, but the swirls will never spontaneously reassemble. The direction is one way only. This same principle applies to everything. A hot pan cools when you take it off the stove, releasing heat into the air. An ice cube melts in warm water, spreading its coldness outward. A broken glass does not reassemble itself. A messy room does not tidy itself. In every case, the reason is the same. There are far more ways for things to be spread out than there are for them to be organized. The universe favors the more probable state, and the more probable state is always higher entropy. The second law is not about disorder in the sense of chaos. It is about probability. When you shuffle a deck of cards, the chances of it ending up in perfect order are astronomically small. There are trillions upon trillions of possible arrangements, and only one of them is a neat sequence from ace to king. The deck will almost certainly end up in a random order, not because chaos is preferred, but because randomness is more likely. Entropy measures this likelihood. High entropy means many possible arrangements. Low entropy means only a few. What made the second law revolutionary was its universality. It did not just apply to engines or coffee, it applied to everything. Chemistry, biology, astronomy, every field of science found the same pattern. Energy spreads, gradients vanish, systems move toward equilibrium, and once equilibrium is reached, nothing more can happen. The system is balanced, stable, and inert. For a long time, the second law was studied on small scales, laboratories, factories, everyday objects. But in the late 19th and early 20th centuries, scientists began to apply it to the universe itself. If entropy always increases, and if the cosmos is a closed system, then the universe as a whole must be heading toward maximum entropy. That realization was the birth of the heat-death hypothesis. The logic was simple but unsettling. Stars burn because they have concentrated fuel. Galaxies shine because they have concentrated matter. Life exists because there are gradients of energy to sustain it. But if entropy keeps rising, those concentrations will eventually spread out. Stars will exhaust their fuel. Galaxies will radiate their energy into space. Gradients will vanish. The universe will reach a state where nothing can change anymore. Heat death. This was not a popular idea at first. Many people found it bleak, even disturbing. The thought that the cosmos might one day grow cold and silent felt like a cosmic tragedy. Some scientists resisted it, searching for loopholes or alternative explanations, but the evidence kept mounting. Every observation confirmed the second law. Energy always spreads. Entropy always rises. The direction is always the same. Over time, the second law became one of the pillars of physics. Albert Einstein once said that it is the only physical theory of universal content which he was convinced would never be overthrown. It is that reliable. From the smallest scales of molecules to the largest scales of galaxies, the pattern holds. Entropy increases. Balance is inevitable. The discovery of the second law also revealed something deeper about time itself. Most physical laws are symmetrical. If you reverse time in the equations, they still work. A ball thrown into the air follows the same path whether the movie plays forward or backward. But entropy breaks that symmetry. It gives time a direction. An arrow. The future is the direction in which entropy increases. The past is the direction where entropy was lower. Without entropy, time would have no preferred flow. This connection between entropy and time is profound. It means that the second law is not just about energy, it is about the structure of reality itself. It is the reason you remember yesterday, but not tomorrow. The reason events unfold in sequence. The reason the universe has a history and a future. Entropy is the drummer, setting the beat, and everything else dances to its rhythm. And so, the second law is the foundation of heat-death. It is the discovery that changed how we see the cosmos. It showed us that the universe is not static, not eternal in its current form. It is a process, a story unfolding in one direction, from concentrated beginnings to dispersed endings, from bright stars to silent stillness, the path is clear. Entropy always rises, and heat-death is where it leads. When scientists first began to imagine the heat-death of the universe, the reaction was not uniform. Some felt awe at the scope of the idea, the way it connected the smallest details of thermodynamics to the ultimate fate of everything. Others felt unease, even dread, at the thought of a cosmos destined for silence. The emotional response to heat-death reveals something deeply human. We are not just observers of the universe, we are participants in it, and the thought of its ending stirs something in us. The phrase heat-death itself first appeared in the mid-1800s, not long after the second law of thermodynamics was formulated. Scientists like Hermann von Helmholtz and William Thomson began to extend the logic of entropy to the cosmos. If energy always spreads, they reasoned, then the universe must eventually run out of usable energy. The stars would fade. The galaxies would grow dark. Everything would reach the same cold temperature, and nothing more could happen. It was a conclusion drawn from the laws of physics, but it felt like a prophecy of doom. The public reaction was mixed. Some people dismissed the idea entirely. The timescales involved were so vast, so far beyond human experience, that they seemed irrelevant. Why worry about something trillions of years in the future when the next century was uncertain enough? Others took it more seriously. seeing in heat death a kind of cosmic nihilism. If the universe itself was doomed, what was the point of anything? Why build? Why create? Why hope if it all ended in cold darkness? Philosophers weighed in as well. Some saw heat death as the ultimate confirmation of impermanence. Nothing lasts, not even the stars. The cosmos is temporary, and so is everything within it. This resonated with certain schools of thought, particularly those emphasizing the transient nature of existence. Others found it troubling, a vision of meaninglessness on the grandest scale. If the universe was heading toward a state where nothing could happen, then perhaps meaning itself was an illusion. Among scientists, the response was more nuanced. Many recognized that heat, death was not a moral statement but a physical prediction. It was the logical outcome of the second law. Nothing more, nothing less. The universe did not care whether humans found the idea comforting or disturbing. It would follow its own laws. Still, even scientists are human, and the emotional weight of the idea was hard to ignore. To imagine a future so distant, so final, so utterly silent, was to confront the limits of existence itself. Some found beauty in the vision. The idea that the universe would not end in violence but in rest had a certain elegance. Heat death was not chaos or destruction. It was equilibrium, the natural conclusion of a process that had been underway since the beginning. Stars shine because they can exhaust themselves. Galaxies glow because they can fade. The universe is alive with drama precisely because it is heading towards stillness. Without that direction, there would be no motion, no life, no story to tell. Others found the idea liberating. If permanence was impossible, then perhaps the goal was never to last forever. Meaning could be found in the moment, in the fleeting beauty of a star's light, in the temporary conditions that allow life to exist. The universe does not need to be eternal to be meaningful. It only needs to be now. But there was also a lingering sadness. The thought that everything we know, everything we love, will one day dissolve into uniformity is not easy to hold. The stars that guide sailors, the constellations that inspire stories, the galaxies that fill telescopes with wonder, all of it will vanish. The night sky will grow dark, the campfires will go out, the cosmos will rest, and there will be no one left to witness it. This emotional complexity is part of what makes heat death such a powerful idea. It is not just a scientific prediction. It is a mirror, reflecting our own relationship with endings. We are creatures who build, who hope, who imagine futures. The thought of an ultimate ending, one that cannot be avoided or delayed, challenges us to think about what we value and why. Some scientists in the early days tried to find ways around heat death. Perhaps the universe was not truly closed. Perhaps new energy could enter from somewhere. Perhaps the laws of thermodynamics did not apply on cosmic scales. But over time, these objections faded. The evidence was too strong. The second law held. Entropy rose. The direction was clear. In the 20th century, as cosmology advanced, the picture became sharper. The discovery of the expanding universe, the measurement of the cosmic microwave background, the observations of distant galaxies, all of it confirmed what thermodynamics had predicted. The universe was not static. It was changing, evolving, heading toward equilibrium. Heat death was not just a philosophical idea. It was the most likely outcome. And yet, the emotional response persisted. Even today, when people first hear about heat death, the reaction is rarely neutral. Some feel wonder at the scale of it. Others feel a kind of existential weight. Still, others feel calm, as if the inevitability of silence makes the noise of daily life less urgent. All of these responses are valid. All of them are part of being human in a universe that is both beautiful and temporary. What is striking is that the idea of heat death does not need to diminish the present. If anything, it can enhance it. To know that stars will not always shine makes their light more precious. To know that galaxies will one day fade makes their glow more remarkable. To know that life exists in a narrow window of cosmic history makes this moment more meaningful. The universe is not less because it ends, it is more because it began. So the first response to heat death, whether awe or unease, is a reflection of what it means to be aware. To know the future is to carry its weight, but it is also to carry its gifts. The knowledge that nothing lasts forever is not a curse. It is a reminder to pay attention, to witness, to appreciate. The stars are shining now. The galaxies are glowing now. We are here now. And that is enough. One of the strangest aspects of heat death is the contradiction it presents. The universe, as far as we can tell, may last forever. Time itself may stretch onward without end, an infinite expanse of moments marching into the future. And yet, light will not. Stars will not shine forever. Galaxies will not glow eternally. The cosmos may be infinite in duration, but it is finite in brightness. This paradox, infinite time but finite light, is at the heart of what makes heat death so unsettling. To understand this contradiction, it helps to think about what infinity means. In mathematics, infinity is not a number. It is a concept, a way of describing something without end. Time, in the current understanding of physics, may be infinite in the future. There is no known process that would stop the clock, no final moment when time itself ceases. The universe may simply continue, moment after moment, stretching forward without limit. But that does not mean the universe will remain the same. Infinite time does not guarantee infinite events. A clock can tick forever, but if nothing changes, the ticking is meaningless. And that is the contradiction. Time may continue, but the things that fill time, stars, galaxies, motion, change, are temporary. They have beginnings and endings. They burn out, fade away, and leave only stillness behind. Consider stars. Each one is a nuclear furnace, fusing hydrogen into helium, releasing energy in the process. This process powers the light we see, the warmth we feel, the gradients that drive everything from weather to life. But fusion requires fuel, and fuel is finite. A star like the Sun has enough hydrogen to last about 10 billion years. Larger stars burn faster, exhausting themselves in mere millions of years. Smaller stars, the red dwarfs, can last trillions of years. But even they will eventually run out. Once the fuel is gone, fusion stops. The star cools. It may collapse into a white dwarf, or explode in a supernova, or fade into a black dwarf over unimaginable spans. But whatever its fate, it will no longer shine. The light that once poured outward, warming planets and lighting the dark, will cease. And once it ceases, it does not return. There is no way to restart a dead star. The fuel is spent, the gradients are gone, and the light is over. Now multiply this by every star in the universe. There are hundreds of billions of stars in the Milky Way alone, and hundreds of billions of galaxies beyond it. Each star is burning its fuel, each one heading toward the same ending. Some will fade sooner, some later, but all will fade. The night sky, crowded with light now, will one day be empty. Not in a sudden blackout, but in a slow dimming, star by star, galaxy by galaxy, until there is nothing left to shine. And yet, time continues. Long after the last star has faded, time will still tick forward. The universe will still exist, stretched across vast distances, but it will be dark. The contradiction is stark. Time may be infinite, but the age of light is not. We live in a temporary era, a brief window in cosmic history when the universe is bright. Before this era, the stars had not yet formed. After this era, they will all be gone. The age of light is sandwiched between darkness and darkness. This raises a profound question. If time continues but nothing changes, is time still meaningful? Physics does not have a clear answer. Some theories suggest that time is inseparable from change. Without events to mark it, time loses its texture, its flow. It becomes an abstract coordinate, existing mathematically but not experientially. Other theories suggest that time continues regardless, ticking onward even in a universe of perfect stillness. Either way, the result is the same. The future may be infinite in duration, but it is empty of activity. The contradiction also touches on the nature of infinity itself. Humans struggle with infinity. Our lives are finite, measured in years. Our cultures are finite, measured in centuries. Even the oldest structures on Earth, mountains, oceans, continents, are finite on cosmic scales. To imagine something lasting forever is almost impossible, and yet the universe may do just that. It may continue long past the point where anything interesting happens, stretching into a future of endless sameness. This is not the infinity of abundance. It is the infinity of emptiness. A universe that lasts forever, but offers nothing new. No stars to be born, no galaxies to collide, no planets to form. Just the same thin radiation, the same cold temperatures, the same uniform silence, repeating without variation across time that never ends. It is infinite, yes, but infinitely quiet. The contradiction is also emotional. Humans often associate infinity with eternity, and eternity with meaning. If something lasts forever, it feels important, significant, worthy. But heat death shows that infinity can be empty. The universe may last forever, but that does not make it eternal in the way we hope. The light, the warmth, the activity, these are what give the cosmos its richness, and these are finite. Perhaps the contradiction is a reminder that meaning does not come from duration. A star does not need to shine forever to be meaningful. It only needs to shine while it can. A galaxy does not need to glow for infinite time to matter. It only needs to glow now. The fact that light is finite does not diminish it. If anything, it makes it more precious. So the contradiction stands. Infinite time, finite light, a universe that may continue forever, but will not always be bright. It is a paradox that challenges us to rethink what we value. Not the endless, but the present. Not the eternal, but the temporary. The stars are shining now. The galaxies are glowing now. Time may be infinite, but this moment is not. And that is what makes it matter. Entropy is one of those words that sounds more complicated than it needs to be. In physics, it is often described as a measure of disorder, but that description can be misleading. Disorder suggests chaos, randomness, a mess. But entropy is not about mess. It is about evenness, about the number of possible arrangements, about the spreading of energy into states that are more probable. Over the years, scientists have debated what entropy truly means, and those debates have shaped our understanding of heat death itself. The earliest definition of entropy came from thermodynamics. In the mid-1800s, Rudolf Clausius defined it mathematically as a way to describe how energy disperses in a system. He showed that in any process, the total entropy of a closed system either stays the same or increases. It never decreases. This was the foundation of the second law, and it pointed to a clear conclusion. The universe is moving toward higher entropy, and the unite endpoint is equilibrium. But what does higher entropy actually look like? One way to think about it is in terms of gradients. A gradient is a difference, a contrast, hot versus cold, concentrated versus dispersed, ordered versus random. Entropy measures the loss of those gradients. When you have a hot object next to a cold one, there is a gradient, and energy can flow. Heat moves from hot to cold, doing work along the way. But once the temperatures equalize, the gradient is gone. Entropy has increased. The system is balanced, and nothing more can happen. This definition works well for engines and laboratories, but when applied to the universe, it raises questions. What does it mean for the cosmos to have high entropy? Is it about temperature? About the distribution of matter? About the uniformity of radiation? Scientists have explored all of these angles, and each one offers a different perspective on what heat death means. One view emphasizes temperature. In this picture, high entropy means that everything reaches the same temperature. Stars are hot, space is cold, and that difference drives everything. But over time, stars radiate their heat into the void. Space warms ever so slightly, and stars cool. Eventually, the temperatures equalize. The universe becomes a uniform, lukewarm expanse, with no hotspots left to power change. This is thermal equilibrium, and it is one way to define heat death. Another view emphasizes structure. Right now, the universe is full of clumps. Stars, galaxies, clusters, all of them are concentrations of matter held together by gravity. But entropy favors spreading. Over time, these structures will dissolve, stars will burn out, galaxies will evaporate, matter will disperse. In the far future, the cosmos will be smooth, featureless, with no clumps left to mark the passage of time. This is structural equilibrium, another face of heat death. A third view emphasizes information. In the 20th century, scientists like Claude Shannon and later Stephen Hawking connected entropy to information. In this framework, entropy measures how much you do not know about a system. A low entropy system is highly ordered, and you can describe it with just a few details. A high entropy system is disordered, and you need far more information to describe every piece. When entropy increases, information is lost, the details blur, the universe forgets. This connection between entropy and information is profound. It suggests that heat death is not just the end of activity, but the end of memory. Every star that ever shone, every galaxy that ever glowed, every planet that ever formed, all of it will be reduced to the same featureless background. The specifics will be erased, smeared out into uniformity. The universe will no longer carry the details of its own history. It will only carry the fact that history happened. Some scientists have pushed this idea even further. If entropy is about information, then perhaps the universe itself is a kind of computation, processing information through physical processes. Stars fuse atoms. Black holes warp space-time. Particles collide, all of it transforming information from one form to another. Heat death, in this view, is the moment when the computation stops. There is no more information to process, no more transformations to perform. The universe has reached its final output, and the program ends. These different views of entropy are not contradictory. They are perspectives, different ways of describing the same underlying reality. Whether you think of entropy as temperature, or structure, or information, the result is the same. The universe is heading toward a state where nothing can change. The gradients vanish, the structures dissolve, the information blurs. Heat death is the endpoint of all these processes. But the debates over entropy also reveal something important. We do not fully understand it yet. Entropy is one of the most fundamental concepts in physics, but it is also one of the most mysterious. Why does it always increase? What does it mean at the quantum level? How does it connect to the arrow of time? these are open questions, and answering them may reshape our understanding of heat death itself. One particularly deep question is whether entropy applies to the universe as a whole. The second law assumes a closed system, a system with no energy coming in or going out. Is the universe truly closed? If it is, then entropy must rise, and heat death is inevitable. But if the universe is open, if there is something beyond it, then the rules might change. Most physicists assume the cosmos is closed, but it is an assumption, not a proven fact. Another question is whether maximum entropy is truly the end. Some theories suggest that even in a state of perfect equilibrium, rare fluctuations might occur. Quantum mechanics allows for randomness, for tiny deviations from the average. Could these fluctuations, over infinite time, create new structures? Could the universe in some sense reboot itself? These ideas are speculative, but they show that our understanding of entropy is still evolving. So, entropy has many faces. It is disorder and evenness. It is the loss of gradients and the spreading of energy. It is the forgetting of information and the end of computation. It is the reason time flows forward and the reason the universe will one day rest. To understand heat death is to understand entropy. And to understand entropy is to grapple with one of the deepest mysteries in all of science. If heat death is the destination, then the journey toward it is already underway. Scientists do not just speculate about the far future. They observe the present, measure the changes, and trace the path the universe is following. Every telescope pointed at the sky, every detector measuring radiation, every calculation of cosmic expansion, all of it is part of an investigation into how the cosmos is fading, and the evidence is clear. The universe is cooling, spreading, and heading toward equilibrium. One of the most important observations came in the early 20th century, when Edwin Hubble measured the light from distant galaxies. He noticed something unexpected. The light was shifted toward the red end of the spectrum, stretched to longer wavelengths. This redshift, as it is called, indicated that galaxies were moving away from us. The farther the galaxy, the faster it receded. Space itself was expanding, carrying galaxies apart like dots on an inflating balloon. This discovery revolutionized cosmology. It showed that the universe was not static but dynamic. If space is expanding now, then it must have been smaller in the past. Tracing the expansion backward leads to the Big Bang, the moment when the universe was incredibly hot and dense, and tracing it forward reveals a cosmos that grows ever larger, ever colder, ever more spread out. Expansion is the engine of heat death, diluting energy across ever greater volumes. Later, in the 1960s, scientists discovered the cosmic microwave background, a faint glow of radiation filling all of space. This glow is the leftover light from the Big Bang, stretched and cooled by billions of years of expansion. When the universe was young, this radiation was scorching, bright enough to ionize atoms. Now, it has cooled to just a few degrees above absolute zero, a faint whisper of the fiery beginning. The cosmic microwave background is direct evidence that the universe is cooling, that energy is spreading thinner and thinner over time. Astronomers also track the fade by studying stars. Every star is a clock, burning its fuel at a measurable rate. By observing stars of different ages and masses, scientists can predict when they will exhaust themselves. The largest stars are already gone, burned out in mere millions of years. Medium stars like the Sun will last billions. The smallest red dwarfs will endure for trillions. But all of them are on the same path. The investigation shows that star formation is slowing. Galaxies are using up their gas, and new stars are becoming rarer. The universe is already past its peak of stellar activity. Even black holes, once thought to be eternal, are part of the investigation. Stephen Hawking's theoretical work on black hole evaporation showed that they radiate energy, slowly losing mass over unimaginable spans. While no one has directly observed Hawking radiation yet, the theory is well supported. If it is correct, then black holes are not final resting places but temporary structures, fading like everything else. The investigation into their behavior continues, with physicists refining the calculations and searching for indirect evidence. The expansion of the universe took another dramatic turn in the late 1990s. Astronomers studying distant supernovae discovered that the expansion is not slowing down, it is accelerating. Some mysterious force, now called dark energy, is pushing galaxies apart faster and faster. This discovery was so unexpected that it took years to accept, but the evidence has held. Dark energy makes up about 70% of the universe, and it is driving the cosmos toward isolation. Galaxies that are far enough away will eventually slip beyond our reach, carried away by expansion faster than light can travel. This acceleration changes the investigation. It means that the universe will not just cool, it will also grow emptier. Galaxies will drift into separate horizons, unable to see one another. The night sky, already dark in most directions, will grow darker still. Eventually, our descendants, if any remain, will see only the stars of their own galaxy. The rest of the cosmos will be invisible, erased by distance. The investigation into dark energy continues, with scientists trying to understand what it is and whether it will remain constant or change over time. Another part of the investigation involves measuring the overall density of matter and energy in the universe. If there were enough matter, gravity might eventually overcome expansion, pulling everything back together in a big crunch. But the measurements show that matter is not dense enough. Combined with dark energy, the cosmos is destined to expand forever. The investigation confirms what thermodynamics predicted. The universe is open, heading toward a state of maximum entropy. Scientists also study the fine details of how energy disperses. They measure the temperature of gas clouds, the brightness of quasars, the distribution of galaxies. Every observation adds to the picture. Energy is spreading, temperatures are equalizing, structures are thinning. The investigation is not about one dramatic discovery, but about the accumulation of evidence, piece by piece, showing that the universe is on a one-way path. Even the study of time itself is part of the investigation. Physicists explore how entropy gives time its arrow, how the increase of disorder creates the sense of past and future. They investigate whether time could exist without change, whether the universe could reach a state where time becomes meaningless. These are not easy questions, but they are essential to understanding what heat death truly means. The investigation is ongoing. New telescopes, new detectors, new theories, all of them contribute to the picture. We do not yet know everything about dark energy, about black hole evaporation, about the ultimate fate of protons. But the trend is clear. The universe is fading. Stars are dimming. Galaxies are drifting apart. Entropy is rising. The investigation tracks the fade, and the fade is real. What makes this investigation remarkable is that it connects the present to the far future. By measuring what is happening now, scientists can predict what will happen trillions of years from now. The laws of physics are consistent, and consistency allows for foresight. The investigation is not guesswork, it is extrapolation, grounded in observation, tested against reality. And every test confirms the same conclusion. The universe is heading towards stillness, and the journey is already underway. Science is built on evidence, and the evidence for heat death is overwhelming. It is not a single observation or one dramatic discovery. It is a tapestry of data woven together from telescopes, detectors, satellites, and centuries of careful measurement. Every thread points in the same direction. The universe is cooling, expanding, and heading toward equilibrium. The data does not lie, and the conclusion is clear. One of the most fundamental pieces of evidence is the redshift of galaxies. When Edwin Hubble measured the light from distant galaxies in the 1920s, he found that it was stretched toward longer wavelengths. The farther a galaxy, the more its light was redshifted. This told him that galaxies were receding, and that space itself was expanding. Decades of additional measurements have confirmed this. The universe is growing larger, and as it grows, the energy within it spreads thinner. The cosmic microwave background provides another crucial data point. Discovered in 1965 by Arno Penzias and Robert Wilson, this faint glow fills all of space. It is the afterglow of the Big Bang, radiation that has been travelling through the universe for nearly 14 billion years. When it was released, it was scorching hot, but expansion has cooled it to just a few degrees above absolute zero. The temperature of this background continues to drop as the universe expands. The data shows a clear trend. The cosmos is getting colder. Observations of stars add to the evidence. Astronomers catalogue stars by type, age, and luminosity. They see that the rate of star formation has been declining for billions of years. Galaxies are running out of the gas needed to form new stars. The data shows that the universe is already past its peak brightness. In the Milky Way alone, the rate of new star births has dropped significantly. The trend is consistent across all observed galaxies. The age of stars is winding down. Measurements of supernova provide yet more evidence. Type Ia supernovae, the explosions of white dwarf stars, are so consistent in brightness that they can be used as cosmic distance markers. In the late 1990s, teams of astronomers used these supernovae to measure the expansion of the universe at different times. The data revealed something shocking. The expansion is not slowing, it is accelerating. This led to the discovery of dark energy, a mysterious force pushing galaxies apart faster and faster. The acceleration means that galaxies will drift beyond reach, isolating themselves from one another. Satellites like the Wilkinson Microwave Anisotropy Probe and the Planck spacecraft have measured the cosmic microwave background with extraordinary precision. They have mapped the distribution of matter, energy in the universe, confirming that dark energy makes up about 70% of the total. This energy does not clump, it does not fade. It simply drives expansion, ensuring that the universe will grow colder and emptier over time. Black holes also contribute to the evidence. While Hawking radiation has not been directly observed, the theory behind it is grounded in well-tested physics. Quantum field theory and general relativity both support the idea that black holes should radiate. The calculations predict that even the largest black holes will eventually evaporate, though on timescales far beyond anything humans can observe directly. The data from particle physics and gravitational wave detections support the underlying principles. Black holes are temporary, not eternal. Another data point comes from the study of galaxy clusters. These are the largest gravitationally bound structures in the universe, containing thousands of galaxies held together by mutual attraction. Observations show that clusters are not forming new ones at the rate they once did. The universe is past the era of rapid structure formation. The data indicates that over time, even clusters will dissolve as galaxies drift apart due to dark energy. The structures we see today are relics, slowly fading. The temperature of intergalactic space is also measurable. It is cold, just a few degrees above absolute zero, but not as cold as it will eventually become. As the universe expands, this temperature will continue to drop. The data shows a steady cooling trend. In the far future, the temperature will approach absolute zero, though it will never quite reach it. Everything will be in thermal equilibrium, with no gradients left to drive change. Even the ages of stars provide evidence. The oldest stars in the universe are about 13 billion years old, formed shortly after the Big Bang. The youngest stars are forming now, but at a much slower rate. The data allows astronomers to predict when the last stars will form and when the last ones will die. Red dwarfs, the smallest and longest-lived stars, will burn for trillions of years. But eventually, even they will exhaust their fuel. The timeline is clear. The age of starlight is finite. The data also includes observations of white dwarfs. These are the remnants of stars like the Sun, no longer fusing but still glowing from residual heat. Astronomers measure their temperatures and track how quickly they cool. The data confirms that white dwarfs radiate their heat into space over billions of years, eventually becoming black dwarfs, cold and dark. While no black dwarfs exist yet, the cooling process is well documented. The evidence points to a future of silent remnants. Gravitational wave detectors like LIGO and Virgo add another layer of evidence. They have observed the collisions of black holes and neutron stars, providing data on how these remnants behave. The observations confirm predictions from general relativity and support the idea that even the most extreme objects follow the same physical laws. Over time, these remnants will either merge or evaporate. The data leaves no exceptions. Everything fades. All of this evidence, from redshift to supernovae, from the cosmic background to black hole theory, paints the same picture. It is evolving, expanding, cooling, and heading toward maximum entropy. The data is not ambiguous. It is clear, consistent, and overwhelming. Heat death is not speculation. It is the logical conclusion of what we observe. The evidence of the end is all around us, written in the light of distant galaxies and the faint glow of the cosmic background. Among all the forces and phenomena shaping the universe, none is more mysterious than dark energy. It is invisible, undetectable except through its effects, and yet it makes up about 70% of everything that exists. It is the force driving galaxies apart, accelerating the expansion of space, and sealing the fate of the cosmos. Dark energy is the deeper mystery at the heart of heat death, and understanding it is key to understanding how the universe will end. The discovery of dark energy was accidental. In the late 1990s, two teams of astronomers were studying distant supernovae, trying to measure how much the expansion of the universe was slowing down. They expected gravity to be pulling galaxies back together, decelerating the growth of space. But the data showed the opposite. The expansion was speeding up. Galaxies were flying apart faster than before. Something was pushing them. At first, the results seemed impossible. Every theory of gravity, from Newton to Einstein, predicted that matter would attract, not repel. Yet the observations were clear. Something was counteracting gravity on cosmic scales, driving expansion faster and faster. The teams checked their data, recalculated, and confirmed the result. The discovery was so unexpected that it earned the researchers the Nobel Prize in Physics. The universe was not just expanding, it was accelerating. Scientists gave this mysterious force a name: dark energy. The term is a placeholder, a label for something we do not yet understand. It is called dark because it does not emit light, and energy because it has effects. But beyond that, we know very little. We do not know what it is made of, where it comes from, or why it behaves the way it does. It is one of the deepest unsolved mysteries in all of science. One possibility is that dark energy is a property of space itself. In Einstein's equations of general relativity, there is a term called the cosmological constant, which represents a kind of inherent energy in the vacuum. Einstein originally added it to keep the universe static, then discarded it when expansion was discovered. But the accelerating expansion revived the idea. Perhaps empty space has energy, and as space expands, more energy is created, driving further expansion. This would explain why dark energy seems constant in density even as the universe grows. Another possibility is that dark energy is a dynamic field, something that changes over time. Physicists call this idea quintessence. Unlike the cosmological constant, which is fixed, quintessence could vary, growing stronger or weaker as the universe ages. If dark energy is dynamic, then the fate of the cosmos might not be heat death at all. It could be something else entirely, perhaps a big rip where space tears itself apart, or a gradual shift into a different state. But so far, the evidence suggests that dark energy is constant, not changing. Whatever dark energy is, its role in heat death is clear. It ensures that the universe will expand forever. Without it, gravity might eventually pull galaxies back together, leading to a big crunch. But dark energy overpowers gravity on large scales, pushing galaxies apart. Over time, this acceleration will carry distant galaxies beyond our horizon, making them invisible. The universe will become not just cold, but also empty, with each galaxy isolated in its own island of space. Dark energy also affects the timeline of heat death. If expansion were decelerating, the universe might take longer to cool, giving stars and black holes more time to radiate. But acceleration speeds the process. It spreads energy across ever larger volumes, diluting it faster. The cosmos is not just fading, it is being stretched thin, hastening the approach of equilibrium. The mystery deepens when you consider the amount of dark energy. It makes up 70% of the universe, yet we cannot see it, touch it, or detect it directly. We only know it exists because galaxies are accelerating apart. This raises profound questions. How can something so dominant be so invisible? Why does it have the exact density it does? If dark energy was slightly stronger, galaxies might never have formed. If it were weaker, gravity might have collapsed the universe long ago. The balance seems fine-tuned, and we do not know why. Some physicists speculate that dark energy is connected to quantum mechanics. The vacuum of space, according to quantum theory, is not truly empty. It is filled with virtual particles popping in and out of existence, borrowing energy for brief moments. This quantum foam, as it is called, might contribute to dark energy. But when scientists calculate the expected energy of the vacuum, the numbers are wildly off, differing from observations by a factor of 10 to the power of 120. This is called the cosmological constant problem, and it is one of the biggest puzzles in physics. Others wonder if dark energy is a sign that our understanding of gravity is incomplete. Perhaps Einstein's equations need modification on cosmic scales. Perhaps there is new physics waiting to be discovered, hiding in the accelerating expansion. These ideas are speculative, but they highlight how little we know. Dark energy is a mystery, wrapped in data, a force we can measure but not explain. For the story of heat death, dark energy is the guarantor. It ensures that expansion continues, that galaxies drift apart, that the universe grows colder and emptier. Without dark energy, the ending might be different. With it, the path is clear. The cosmos will expand forever, spreading its energy thinner and thinner until nothing remains but uniform stillness. Dark energy is the deeper mystery, the force shaping the far future, the invisible hand guiding the universe toward its final rest. There will come a time, trillions of years from now, when the last stars exhaust their fuel and fade into darkness. This moment, distant as it is, represents a turning point in the history of the universe. It is the transition from an age of light to an age of shadows, from a cosmos alive with energy to one dominated by remnants. The fading of the last stars is not the end of everything, but it is the end of an era, and it marks the beginning of the long descent toward heat death. Right now, stars are everywhere. The Milky Way alone contains hundreds of billions of them, and there are hundreds of billions of galaxies beyond. Stars shine in every corner of the observable universe, filling space with light and warmth. But star formation is slowing. Galaxies are running out of gas, the raw material needed to ignite new suns. The universe is already past its peak of stellar activity. The brightest, most massive stars lived and died long ago. What remains now are the smaller, longer-lived stars, and even they are on borrowed time. The last stars to burn will be the red dwarfs, the smallest and dimmest of all. These stars are so faint that none are visible to the naked eye, yet they are by far the most common type in the universe. Red dwarfs burn their fuel incredibly slowly, sipping hydrogen over trillions of years. While massive stars blaze through their lives in millions of years, red dwarfs endure. They are the tortoises of the stellar world, patient and persistent. But even tortoises reach the finish line. In about 10 trillion years, the last red dwarfs will begin to sputter out. By that time, the universe will be unrecognizable. The cosmic microwave background will have cooled to nearly nothing. Galaxies will have drifted so far apart that most will be invisible to one another. The night sky, once crowded with stars, will be nearly empty. Only a few faint red dwarfs will remain, glowing weakly in the darkness, the last campfires of the cosmos. As each red dwarf exhausts its fuel, it will shrink and cool, becoming a white dwarf. These remnants will glow faintly for a time, radiating the last of their stored heat into space. But without fusion to sustain them, they will grow dimmer and dimmer, eventually fading to black. The turning point is not a single moment but a slow transition, star by star, until the age of starlight is over. Imagine standing on a planet orbiting one of the last red dwarfs. The sky above would be almost completely dark. The galaxies that once filled the heavens would be gone, carried beyond the horizon by expansion. Only your star would remain, a faint red glow, barely enough to warm the surface. And then, one day, even that would fade. The sun would cool, the light would dim, and the sky would go black. The turning point would have passed, and the age of remnants would begin. This transition is significant because it marks the loss of the last major source of energy in the universe. Stars are not just sources of light, they are engines of creation. Inside their cores, they fuse hydrogen into helium, helium into carbon, carbon into heavier elements. These elements, scattered into space when stars die, become the building blocks of planets, life, and everything we know. Without stars, no new elements are forged. The chemistry of the cosmos freezes, locked into whatever forms it has already taken. The fading of the last stars also means the end of habitable zones. Life, as we know it, requires energy gradients. It needs a warm star nearby, a planet at the right distance, and chemistry that can harness the flow of energy. When the stars go out, those conditions vanish. Any life still clinging to existence will face an impossible challenge. The universe will be too cold, too dark, too empty to sustain it. The turning point is not just the end of light, but the end of the possibility of life. After the last stars fade, the universe will be filled with remnants, white dwarfs, cooling slowly over billions of years. Neutron stars, dense and dark. Black holes, sitting silently at the centers of what used to be galaxies. These objects will drift through the void, occasionally colliding, occasionally merging, but mostly alone. The turning point is the shift from a universe of active processes to a universe of passive waiting. The psychological weight of this turning point is profound. It is the moment when the universe crosses a threshold it can never return from. Stars, once gone, do not reignite. There is no second act, no encore. The age of light is over, and what follows is darkness. For billions of years, the cosmos has been defined by stars. They have been the markers of distance, the sources of energy, the anchors of galaxies. Without them, the universe becomes a different place. Quieter, colder, emptier. Yet the turning point is also a kind of completion. Stars were never meant to last forever. They were always temporary, burning fuel that would one day run out. The fading of the last stars is not a failure. It is the natural conclusion of a process that has been underway since the first stars ignited billions of years ago. The turning point is not an ending in the dramatic sense, but a transition, the closing of one chapter and the opening of another. And so, in about 10 trillion years, the last stars will fade. The night sky will grow dark, the age of light will end, and the age of remnants will begin. The turning point will pass, and the universe will take another step towards stillness. The campfires of the cosmos will have gone out, and only ashes will remain. When the last stars have faded, the universe does not end. It continues, but in a form almost unrecognizable from what we see today. What remains is a cosmos filled with remnants, the cold echoes of objects that once burned brightly. White dwarfs, neutron stars, and black holes drift through the darkness, monuments to a time when energy flowed and light filled the sky. This is the consequence of the turning point, the immediate aftermath of the age of stars, a universe of remnants, silent and still. White dwarfs will be the most common remnants. These are the cores of stars like the sun, left behind after the outer layers have blown away. They are about the size of Earth but contain roughly half the mass of the sun, making them incredibly dense. A teaspoon of white dwarf material would weigh tons. When they first form, they glow brightly, radiating the heat left over from their stellar lives. But without fusion to sustain them, they cool slowly, dimming over billions and trillions of years. In the universe of remnants, white dwarfs will fill the space where stars once shone. They will drift through galaxies, invisible except for their faint glow. Over time, that glow will fade. The white dwarfs will cool from white to yellow to red, eventually becoming black dwarfs, objects so cold they emit no light at all. The universe is not yet old enough for black dwarfs to exist, but in the far future, they will dominate. Silent, dark, and inert, they will be the ghosts of suns. Neutron stars will also remain. These are the remnants of more massive stars, compressed by gravity into spheres only a few miles across. They are even denser than white dwarfs, with matter so tightly packed that a teaspoon would weigh as much as a mountain. Some neutron stars spin rapidly, emitting beams of radiation as pulsars. But over time, they slow down. Their rotation decreases, their emissions weaken, and they fade into silence. In the universe of remnants, neutron stars will be scattered across the void, dark and cold. Black holes will be the largest remnants, formed from the collapse of the most massive stars or from the centers of galaxies. They are regions of space-time so warped that nothing, not even light, can escape. Black holes do not shine, but they do have mass, and that mass shapes the space around them. In the remnant universe, black holes will sit at the centers of what used to be galaxies, surrounded by the dark husks of white dwarfs and neutron stars. Occasionally, one of these remnants will drift too close and be swallowed, but mostly they will simply orbit, alone in the dark. The consequence of this transition is profound. The universe will no longer be a place of activity. There will be no fusion, no explosions, no new elements being forged. The processes that filled the cosmos with complexity will have ceased. What remains is a graveyard, a collection of objects that no longer change, no longer interact in meaningful ways. The energy that once flowed freely is now locked away, spread too thin to drive anything new. Galaxies themselves will have changed. Right now, they are held together by gravity, bound systems of stars orbiting a common center. But over trillions of years, Gravitational interactions will slowly eject stars and remnants into intergalactic space. Some will drift outward, escaping the galaxy entirely. Others will spiral inward, feeding the central black hole. Bit by bit, galaxies will evaporate, losing their members until only the black hole remains, surrounded by a faint halo of stragglers. This process is called dynamical relaxation, and it is slow, unimaginably slow. It takes longer than the current age of the universe by a factor of thousands or more. But time is not in short supply. The consequence is that even the structures we think of as permanent, galaxies, clusters, are temporary. They too will dissolve, their remnants scattered across the void. The universe of remnants will be lonelier than the universe of stars. The darkness will be profound. Right now, the night sky is filled with light, even if our eyes cannot see most of it. Infrared, ultraviolet, radio waves, all of it pours through space, carrying information about stars and galaxies. But in the universe of remnants, that light will be gone. The cosmic microwave background will have cooled to nearly nothing. The faint glow of white dwarfs will have faded. Black holes do not emit visible light. The universe will be darker than any night you have ever experienced. Yet even in this darkness, there will still be motion. Remnants will orbit. Black holes will occasionally merge, releasing bursts of gravitational waves. White dwarfs might collide, briefly flaring before fading again. These events will be rare, separated by vast stretches of time and space, but they will punctuate the stillness. The consequence is not total silence, but something close. A universe where events are so infrequent they may as well not exist. The psychological impact of imagining this consequence is heavy. To picture a cosmos filled with the remnants of everything that once was, to see stars reduced to cold embers, galaxies dissolved into scattered debris, is to confront the impermanence of everything. The universe does not preserve. It transforms, and in transforming, it loses. The stars that once shone will be gone, and what remains will be only the memory of their existence, encoded in the positions and masses of remnants. But the consequence is also a continuation. The universe has not vanished. Energy has not disappeared. The laws of physics still hold. The remnants are still matter, still governed by gravity, still part of the cosmic story. They are not nothing. They are the next chapter, the stage that follows the age of light. The universe of remnants is the consequence of the turning point, the immediate result of stars fading. It is not the end, but it is a step closer to stillness. And so, in the far future, the cosmos will be filled with remnants. White dwarfs cooling in the dark, neutron stars drifting silently, black holes sitting alone at the centers of empty galaxies. The consequence is a universe transformed, quieter, colder, and emptier, but still existing. The story continues, even as the light fades. In the universe of remnants, something strange happens to time. Without stars shining, without galaxies colliding, without new processes unfolding, the flow of time begins to lose its meaning. Events become so rare, so scattered, that the distinction between one moment and the next blurs. The impact of this transformation is profound. Time, which has always been the river carrying the universe forward, becomes still, not because it stops, but because there is nothing left to mark its passage. By change. A second is measured by the vibration of atoms. A day is marked by the rotation of Earth. A year is one orbit around the sun. History is the sequence of events, the before and after that gives life its narrative structure. But all of these measurements depend on processes, on things happening. In the universe of remnants, processes slow to a crawl. The distinction between past and future fades. Imagine standing in a place where nothing ever changes, No sunrise, no sunset, no seasons, no growth, no decay. How would you know that time was passing? You might count in your head, but eventually even that would blur. Without external markers, time becomes invisible. In the far future, the universe will be like that. The remnants will drift, but their motion will be so slow, so uniform, that it is almost imperceptible. Nothing distinguishes 1 trillion years from the next. This is what physicists mean when they talk about the arrow of time. The arrow is the direction in which entropy increases. It is the reason you remember yesterday but not tomorrow, the reason eggs crack but do not uncrack. Entropy gives time its flow, its sense of forward motion, but when entropy reaches its maximum, when the universe is in equilibrium, the arrow disappears. There is no longer a preferred direction. The future looks the same as the past because nothing changes. The impact of this is not just philosophical, it touches the very nature of reality. Time is woven into the fabric of space-time, inseparable from the 3 dimensions of space. Einstein showed that time can stretch or compress depending on gravity and velocity. But even Einstein's equations assume that time is a dimension along which events can be ordered. If events cease, does time itself become meaningless? Some physicists argue that time is an illusion, a byproduct of entropy. In this view, time does not exist independently. It is simply the way we perceive the increase of disorder. When entropy stops rising, time stops having significance. The universe still exists, but it is frozen in a state of unchanging uniformity. Time becomes a mathematical coordinate with no physical relevance. Others argue that time continues regardless of whether anything happens. The universe could sit in equilibrium for infinite duration, and time would still tick onward even if there were no events to mark it. In this view, time is fundamental, not emergent. It exists whether or not we can measure it. The impact, then, is not the end of time, but the end of time's usefulness. Either way, the result is the same from an experiential standpoint. In a universe without events, time loses its texture. It becomes smooth, featureless, indistinguishable. You could fast forward 1 trillion years, and nothing would have changed. The remnants would still be drifting, the black holes would still be sitting in silence, the temperature would still be uniform. Time without events is time without meaning. This has implications for the concept of existence itself. To exist is usually understood as being present in time and space, participating in the flow of moments. But if time loses its flow, what does existence mean? The remnants still have mass. They still occupy space, but they do not change, do not interact, do not evolve. Are they still part of a living universe, or are they simply artifacts, frozen in a timeless void? The impact of time without events also touches on the nature of observation. In our current universe, time can be measured because there are observers. Humans measure it with clocks. Stars measure it by burning fuel. Atoms measure it by vibrating. But in the far future, there will be no observers. No life, no consciousness, no minds to mark the passage of moments. If time passes, but no one observes it, does it still have reality? Quantum mechanics adds another layer to this question. In quantum theory, observation plays a role in determining outcomes. The act of measurement collapses possibilities into certainties. But in a universe without observers, without measurements, quantum states might remain perpetually undefined. The impact is a cosmos that exists but does not resolve, a universe suspended in potential without actuality. There is also the question of rare fluctuations. Even in a universe of maximum entropy, quantum mechanics allows for random variations. A particle might briefly appear, a field might fluctuate, a tiny deviation from equilibrium might occur. These events would be extraordinarily rare, separated by spans so vast they are almost incomprehensible. But they would still be events. And if events still occur, then time, in some sense, still has meaning. The impact is not absolute stillness, but near stillness, a universe where time crawls so slowly it is almost undetectable. This raises a paradox. If time continues but events are infinitely rare, then from the perspective of any hypothetical observer, time would seem to have stopped. But from the perspective of the universe itself, time would still be flowing, just without content. The impact is a duality, time that exists but does not matter, a dimension that persists but carries nothing. The emotional weight of this impact is strange. It is not the end of existence, but the end of narrative. The universe will still be there, but its story will have finished. There will be no new chapters, no surprises, no developments, just a long, unchanging present stretching into infinity. The impact of time without events is the transformation of the cosmos into a monument, a frozen tableau of what once was. And so, as the universe of remnants settles into stillness, time loses its grip. The arrow fades. The flow slows to nothing. Events become so rare they are meaningless. The impact is profound. Time, which has carried the cosmos from the Big Bang to the age of stars, will finally rest, not because it ends, but because there is nothing left for it to carry. History, humanity occupies a remarkable position. We are not at the beginning, when the universe was too simple and chaotic to support complexity. We are not at the end, when it will be too cold and empty to sustain life. We are in the middle, in the luminous window, when stars still shine and galaxies still glow. To be alive now, in this brief era, is to be witnesses to the universe at its most vibrant. This is the human element in the story of heat-death, the realization that we exist in a rare and precious moment. The universe is approximately 13.8 billion years old. That sounds ancient, but compared to the timescales of heat-death, it is young. The stars will continue to burn for trillions of years. Black holes will persist for unimaginable spans beyond that. The universe may exist, in some form, for infinite duration. Against that backdrop, the current age is fleeting. We live in the opening act of a story that will stretch far beyond comprehension. What makes this position special is that the universe is still full of structure. Galaxies spiral with billions of stars. Nebulae glow with the light of newborn suns. Planets orbit in stable systems. Chemistry allows for complexity. Life has arisen, at least on Earth, and perhaps elsewhere. The conditions that make all of this possible are temporary. They depend on stars, and stars depend on fuel. Once the fuel is gone, the conditions vanish. We live in the narrow window when the cosmos supports richness. Humanity did not choose to exist now. It is an accident of timing, a result of the universe's evolution. Stars had to form first, scattering heavy elements into space. Planets had to coalesce from those elements. Life had to evolve, slowly, over billions of years. By the time humans appeared, the universe was already old, but it was still young enough to be bright. We are witnesses to the middle because the middle is the only time when witnesses can exist. This perspective changes how we see ourselves. It is easy to feel small and insignificant in the face of the cosmos. The universe is vast, and we are tiny. Our lives are brief, and the stars are ancient. But rarity is a form of significance. To exist in the luminous middle is to be part of something extraordinary. The universe will spend most of its existence in darkness. We are alive in the age of light. Consider what we can see. On a clear night, far from city lights, you can look up and see the Milky Way stretching across the sky. That band of light is made of billions of stars, each one a sun in its own right. You can see other galaxies, faint smudges of light that are entire worlds unto themselves. You can see the light of stars that have been travelling for thousands of years to reach your eyes. All of this is only possible because we live in the middle. In the far future, observers, if any existed, would see none of this. The galaxies would have drifted beyond view. The stars would be gone. The sky would be empty. The human element also includes the ability to understand. We are not just witnesses. We are conscious witnesses, capable of asking why and how. Through science, we have traced the history of the universe from the Big Bang to the present. We have measured the expansion of space, the cooling of the cosmic background, the fading of stars. We have imagined the far future, calculated the timescales, and predicted the eventual silence. This understanding is itself part of the story. The universe has become aware of itself, briefly, through us. This awareness does not change the outcome. Heat death will arrive whether we understand it or not, but it changes the journey. For a brief time, the cosmos is not just matter and energy, it is also thought, wonder, and curiosity. The human element is the universe reflecting on its own fate. That reflection is fragile and temporary, but it is real. It adds a layer of meaning that the cosmos would not otherwise have. The human element also includes the emotional response. We feel awe at the scale of the universe. We feel sadness at the thought of its ending. We feel wonder at the fact that we exist at all. These emotions are part of the story too. They show that we are not separate from the cosmos but deeply connected to it. The atoms in our bodies were forged in stars. The energy that powers our thoughts came from the sun. We are not outside observers. We are participants. To be witnesses to the middle is also to carry a responsibility. Not a cosmic responsibility. The universe does not need us, but a human one. To witness is to pay attention, to notice, to appreciate. The stars are shining now. The galaxies are glowing now. This moment, with all its richness, is fleeting. The human element is the choice to see it, to honour it, to carry it forward in memory and understanding for as long as we can. There is also humility in this position. We are not special in the sense of being central or chosen. The universe does not revolve around us, but we are special in the sense of being rare. Life, consciousness, the ability to ask questions, these are not common features of the cosmos. They may be extraordinarily rare, perhaps unique. To exist in the middle, with all the conditions aligned, is an improbable gift. And so, the human element in the story of heat death is this. We are here, now, in the luminous middle. We are witnesses to a universe still alive with energy and structure. We can see the stars, understand the laws, and imagine the ending. This makes us part of the cosmic story, a brief chapter in a long narrative. The universe will continue without us, fading into silence over eons. But for now, we are here, and that is enough. Heat death is the most widely accepted vision of how the universe will end, but it is not the only possibility. Science thrives on questioning, on exploring alternatives, and over the years, physicists have proposed several different endings for the cosmos. Each one is grounded in observation and theory, but each depends on different assumptions about the nature of dark energy, matter, and the laws of physics. These alternatives, the Big Rip, the Big Crunch, and cosmic bounces, offer different visions of finality. They are the opposition to heat death, and exploring them sharpens our understanding of why heat death remains the leading theory. The Big Rip is perhaps the most violent of the alternatives. It begins with the same observation that led to dark energy. The expansion of the universe is accelerating. Galaxies are flying apart faster and faster. But what if dark energy is not constant? What if it grows stronger over time? In that case, The acceleration would not just separate galaxies, it would eventually tear them apart. Stars would be ripped from galaxies. Planets would be torn from stars. Eventually, even molecules and atoms would be shredded by the expanding fabric of space itself. The Big Rip would arrive in a finite future, perhaps tens of billions of years from now, depending on how dark energy evolves. Unlike heat death, which unfolds over trillions upon trillions of years, the Big Rip would be sudden. There would be a final moment when space-time itself fractures, when the forces holding matter together are overwhelmed by expansion. The universe would end not in silence but in tearing, a cosmic shredding that leaves nothing intact. The idea is dramatic, almost catastrophic, but it depends entirely on dark energy behaving in a way we have not observed. Current measurements suggest that dark energy is constant, a property of space that does not change. If that remains true, the Big Rip will not happen. Heat death will prevail, but the possibility cannot be ruled out entirely. Dark energy is still mysterious, and surprises are possible. The Big Rip is the opposition that reminds us how much we do not yet know. The Big Crunch offers a different kind of ending. Instead of expansion continuing forever, imagine that gravity eventually wins. If there were enough matter in the universe, its collective pull might slow the expansion, halt it, and then reverse it. Galaxies would begin to draw closer. Space would contract. The cosmic microwave background would heat up instead of cooling. Everything that had spread apart would come rushing back together. The Big Crunch would mirror the Big Bang in reverse. As space contracted, temperatures would rise, stars would merge, galaxies would collide. Eventually, everything would compress into a singularity, a point of infinite density. The universe would end not in cold silence but in fiery collapse. Some versions of this idea suggest that the crunch might trigger a new Big Bang, creating a cyclic universe that expands and contracts forever. The Big Crunch was once a serious contender. Before the discovery of dark energy, many cosmologists assumed that gravity would slow expansion. The question was whether there was enough matter to reverse it. But observations in the late 1990s changed everything. Not only is expansion not slowing, it is accelerating. There does not appear to be enough matter to reverse the trend, and dark energy is pushing galaxies apart, not pulling them together. The Big Crunch, while elegant, is now considered unlikely. Heat death fits the data better. The idea of a cosmic bounce takes the Big Crunch one step further. Instead of ending in a singularity, the universe might rebound. Quantum effects, or some unknown property of space-time, might prevent the collapse from becoming infinite. At the moment of maximum compression, the universe could bounce back, triggering a new expansion. This would create a cycle, an eternal sequence of expansions and contractions with no true beginning or end. The bounce is appealing because it avoids the finality of heat death. Instead of silence, the universe continues, renewing itself endlessly. It resonates with ancient ideas of cyclical time, found in many cultures, philosophies. But like the Big Crunch, the bounce depends on physics we do not fully understand. Quantum gravity, the theory that should describe what happens at extreme densities, is still incomplete. Until we have that theory, the bounce remains speculative. Heat death, which requires no new physics, remains more plausible. There are other alternatives as well. Some physicists speculate about the multiverse, the idea that our universe is one among many, each with its own fate. Others imagine that dark energy might decay, changing the trajectory of expansion. Still others propose that the universe could undergo a phase transition, shifting into a different state entirely. These ideas are fascinating, but they are not yet supported by strong evidence. Heat death, grounded in thermodynamics and confirmed by observation, remains the default. What makes these alternatives valuable is that they highlight the uncertainty. We do not know everything about the universe. Dark energy is still a mystery. Quantum gravity is still unsolved. The fate of the cosmos depends on details we have not yet measured. The opposition to heat-death is not just competing theories. It is a reminder that science is a process, always open to revision. But among all the possibilities, heat-death stands out for its consistency. It does not require dark energy to change. It does not require new physics to emerge. It simply requires the laws we already know to continue working. Entropy increases. Energy spreads. Gradients vanish. The universe reaches equilibrium. That is heat-death, and it is the ending that best fits what we observe. So the opposition exists, and it is worth exploring. The big rip, the big crunch, the bounce, they all offer different endings, each with its own logic and appeal. But heat-death remains the leading theory, the most likely fate, the vision that best explains where the universe is heading. The opposition sharpens the argument, but it does not overturn it. Heat-death is still the path, and the cosmos is still walking it. To truly grasp heat-death is to awaken to the universality of entropy. It is to see the same principle at work in a melting ice cube and a fading galaxy, in a cooling cup of coffee and the evaporation of a black hole. Entropy is not just a law written in textbooks. It is the rhythm of reality, the pattern that governs everything from the smallest scale to the largest. Understanding entropy is the awakening, the moment when the pieces fall into place and the story of heat-death becomes clear. Entropy is often described as disorder, but that description misses the deeper truth. Entropy is about probability. When you have a system with many parts, there are usually far more ways for those parts to be spread out evenly than there are for them to be organized. A deck of cards shuffled is almost never in perfect order, because there is only one ordered arrangement and trillions of random ones. Entropy measures this likelihood. High entropy means many possible arrangements. Low entropy means only a few. The awakening comes when you realize that this principle applies everywhere. Consider your room. If you leave it alone, it tends to get messier over time. Clothes pile up, books scatter, dust accumulates. This is not because disorder is preferred, but because there are far more ways for things to be messy than tidy. The same principle governs molecules in a gas. They spread out to fill a container because there are more ways to be spread than clumped. Entropy is the tendency toward the more probable state. In the universe, this tendency is relentless. Energy starts concentrated in stars, in galaxies, in gradients of heat. But over time, it spreads. Stars radiate their light into space. Heat flows from hot to cold. Radiation stretches as the universe expands. Every process moves toward higher entropy, toward more evenness. The awakening is seeing that this is not chaos. It is balance. The universe is not falling apart. It is settling into equilibrium. The second law of thermodynamics codifies this truth. It says that in a closed system, entropy always increases. It never decreases on its own. You can temporarily lower entropy in one place by expending energy, like cleaning your room or building a structure. But the overall entropy of the system, including the energy you used, always goes up. The universe, as far as we know, is the ultimate closed system. There is nothing outside it to pump fresh energy in. So, entropy rises, and it will keep rising until it reaches its maximum. The awakening also reveals the connection between entropy and time. Time feels like it flows in one direction, from past to future. You remember yesterday, but not tomorrow. Eggs crack, but do not uncrack. Rivers flow downhill, not uphill. All of these asymmetries are explained by entropy. The future is the direction in which entropy increases. The past is the direction where it was lower. Without entropy, time would have no arrow. It would be just another dimension with no preferred direction. Entropy is what makes time feel real. This connection is profound. It means that the second law is not just about energy. It is about the structure of reality itself. It is the reason the universe has a history, a narrative, a sequence of events. The Big Bang was a state of low entropy, highly ordered, full of potential. Everything since then has been a move toward higher entropy, toward spreading, toward balance. Heat death is the endpoint, the moment when entropy is maxed out and the arrow of time loses its meaning. Understanding entropy also explains why some processes are irreversible. You can burn a log, turning it into ash and smoke, but you cannot gather the ash and smoke and turn them back into a log. The process is one way because the burned state has higher entropy. The molecules are more spread out, the energy more dispersed. Reversing it would require lowering entropy, which violates the second law. The burned state has higher entropy. Universe does not allow it. The same logic applies to the cosmos. Stars burn their fuel, radiating energy into space. That process is irreversible. Once the fuel is spent, it cannot be regathered. Black holes evaporate, releasing radiation. That process, too, is one way. The universe is full of irreversible processes, all moving in the same direction, all increasing entropy. The awakening is realizing that this direction is universal. From the smallest particle to the largest galaxy, the pattern holds. There is also beauty in this understanding. Entropy is not an enemy. It is not something that destroys or diminishes. It is the principle that makes change possible. Without entropy, nothing would happen. There would be no flow of energy, no gradients to drive motion, no processes to transform matter. Stars shine because entropy allows fuel to burn. Life exists because entropy allows energy to flow from the sun to Earth. The universe is alive with activity precisely because it is, heading toward stillness. The awakening also brings perspective. If entropy is universal, then impermanence is built into the fabric of reality. Nothing lasts forever. Not stars, not galaxies, not even black holes. Everything is temporary, a passing configuration on the way to equilibrium. This does not diminish the value of things. If anything, it enhances it. The stars are shining now, and that is what matters. They will not shine forever, but they are shining now. Understanding entropy also dissolves some of the fear around heat death. It is not a catastrophe. It is a completion. The universe is not being destroyed. It is reaching its natural end state. Entropy is not punishment or failure. It is the law, the rhythm, the way things work. Heat death is simply entropy fulfilled, the cosmos arriving at the most probable state. And so, the awakening is this: entropy governs everything. It is the reason ice melts, stars fade, and the universe heads toward silence. It is the arrow of time, the driver of change, the pattern behind all patterns. To understand entropy is to see the universe clearly, to grasp the inevitability of heat death, and to recognize that this inevitability is not tragic. It is simply the way things are. The awakening is acceptance, understanding, and peace. For a long time, black holes seemed like the ultimate survivors. They are the densest objects in the universe, regions of space-time so warped that nothing, not even light, can escape. They swallow stars, consume gas, and grow ever larger. They seemed eternal, the final resting places of matter, immune to the processes that destroy everything else. But then came a revelation, one that changed how we see the cosmos. Even black holes vanish. They are not eternal. They evaporate, slowly, patiently, over time scales that defy comprehension. This is the revelation at the heart of heat death. The realization that nothing, Not even the mightiest structures can escape entropy. The revelation came from Stephen Hawking in the 1970s. Hawking was studying the intersection of quantum mechanics and general relativity, two pillars of physics that do not always fit together smoothly. He asked a simple question: what happens at the edge of a black hole, the event horizon, where quantum effects might become important? The answer he found was astonishing. Black holes are not perfectly black. They radiate. The process is subtle. Near the event horizon, quantum mechanics allows for pairs of particles to appear briefly from the vacuum, borrowing energy for a fleeting moment. Normally, these pairs annihilate each other almost instantly, but near a black hole, something different can happen. One particle might fall inside while the other escapes. If that happens, the escaping particle becomes real, carrying energy away. To conserve energy, the black hole must lose a tiny bit of mass. This is Hawking radiation, and it means that black holes slowly evaporate. The revelation was shocking because it overturned the assumption of permanence. Black holes are not eternal traps. They leak. Over unimaginable spans, they shrink, and eventually, they vanish. The timescales are staggering. A black hole the mass of the Sun would take about 10 to the power of 67 years to evaporate. A supermassive black hole, millions or billions of times heavier, would take up to 10 to the power of 100 years. These numbers are so large they lose connection to intuition. But the principle is clear. Black holes have lifetimes, and those lifetimes are finite. The revelation also resolved a paradox. If black holes were eternal, they would be repositories of information, locked away forever. But quantum mechanics says that information cannot be destroyed. Hawking radiation provides a way out. As the black hole evaporates, the information it swallowed might be encoded in the radiation, released back into the universe. The details are still debated, but the revelation shows that black holes are not exceptions to the rules. They follow the same laws as everything else. For the story of heat death, this revelation is crucial. Black holes are the last great structures, the final concentrations of mass in a universe that has already faded. If they were eternal, the cosmos might always contain some form of structure, some anchors in the void. But Hawking radiation says otherwise. Even black holes will vanish, and when they do, the universe will be left with nothing but thin radiation, spread evenly across space. The revelation ensures that heat death is complete, that no structures survive, that equilibrium is truly final. Imagine the timeline. In the far future, long after stars have faded and galaxies have dissolved, black holes will dominate. They will sit in the dark, massive and silent, the last remnants of everything that once was. For eons, they will seem unchanging, patient, eternal. But slowly, imperceptibly, they will radiate. Bit by bit, they will lose mass. The process is so gradual that it might as well be invisible, but it never stops. As a black hole shrinks, it heats up. The smaller it gets, the faster it radiates. In its final moments, it releases a burst of energy, a brief flare in the darkness. Then it is gone, leaving only the faint radiation it emitted, spreading into the void. The revelation is that this fate awaits every black hole, no matter how large. The giants at the centers of galaxies, the stellar remnants scattered across space, all of them will evaporate. All of them will vanish. The emotional weight of this revelation is profound. If even black holes cannot last, then truly nothing can. The universe has no permanent fixtures, no eternal anchors. Everything is temporary, a passing configuration on the way to equilibrium. The revelation strips away the last illusion of permanence and shows that the cosmos is entirely subject to the second law. Entropy wins, always, everywhere, without exception. But the revelation also has a kind of beauty. It shows the consistency of the universe. The same laws that govern melting ice and cooling coffee also govern black holes. There are no exceptions, no special cases. The universe plays fair. From the smallest particle to the largest black hole, the rules are the same. The revelation is not just about black holes. It is about the universality of physics, the reliability of natural law. Hawking radiation also connects to the nature of information and memory. If black holes evaporate and release their information, then the universe does not forget entirely. The details may be scrambled, encoded in radiation too faint to decode, but they are not erased. The revelation suggests that the cosmos carries its history, even in its final state. The memory of stars, of galaxies, of everything that once was, might be preserved in the faint whispers of radiation left behind. There is also something poetic in the idea that black holes, the objects that seem most final, are themselves temporary. They are not the end of the story. They are just another chapter, another stage in the long journey toward equilibrium. The revelation is that the universe does not stop with black holes. It continues past them, beyond them, into a future of even greater stillness. And so, the revelation is this: even black holes vanish. They radiate, they shrink, and they disappear. No structure is eternal. No concentration of mass survives forever. The universe, in the end, will be left with nothing but uniformity, nothing but the faint echoes of everything that once was. The revelation is the final confirmation of heat death, the last piece of the puzzle. Nothing escapes, nothing lasts. The cosmos heads towards silence, and even the mightiest giants bow to entropy. After following the universe from the brilliance of stars to the silence of heat death, it is worth pausing to reflect. What does it all mean? Not in a cosmic sense. The universe does not assign meaning, but in a human sense. What do we take from this story of fading light, spreading energy, and inevitable stillness? The reflection is personal, quiet, and perhaps different for each of us. But there are common threads, ideas that emerge when we sit with the enormity of heat death and ask what it says about existence. The first reflection is about impermanence. Nothing lasts forever. Stars burn out, galaxies dissolve, black holes evaporate. Even the universe itself, vast and ancient as it is, will one day reach a state where nothing more can happen. Impermanence is built into the fabric of reality. It is not a flaw or a failure. It is simply the way things are. The second law of thermodynamics ensures it. Entropy always rises. And rising entropy means that structures are temporary, that gradients fade, that everything moves toward equilibrium. This impermanence can feel unsettling. Humans build, create, and hope for things to endure. We construct monuments, write books, record, memories. We want our lives to matter, to leave a mark. But the reflection on heat death shows that permanence is not the measure of meaning. The stars do not need to shine forever to be meaningful. They only need to shine while they can. A sunset does not lose its beauty because it fades. A song does not lose its power because it ends. Meaning is found in the moment, not in eternity. The second reflection is about scale. The time scales of heat death are so vast they stretch beyond comprehension. Trillions of years, quadrillions, numbers with 100 zeros. These spans make human lifetimes vanishingly small. Your entire life, from birth to death, is a flicker in cosmic terms. Civilizations rise and fall in moments. Even recorded history is a thin sliver compared to the age of the universe. The reflection on scale can be humbling, but it can also be liberating. If the universe itself is temporary, then perhaps the weight of our mistakes, our failures, our regrets is lighter than we think. The third reflection is about the present. Heat death lies in the far future, so distant it is almost abstract. But the present is real. Right now, stars are shining, galaxies are glowing, the sun is warming Earth, life is flourishing. The conditions that make all of this possible are temporary. Yes, but they exist now. The reflection is that this moment, this luminous middle, is the one that matters. The future may be silent, but the present is alive. And that is enough. The fourth reflection is about connection. We are not separate from the universe. We are part of it, made of the same matter, governed by the same laws. The atoms in your body were forged in stars that lived and died billions of years ago. The energy that powers your thoughts came from the sun, which came from fusion, which came from gravity, which came from the Big Bang. You are a temporary arrangement of cosmic elements, a brief pattern in the flow of entropy. The reflection is that to exist at all is to be woven into the fabric of the universe. You are not outside the story, you are in it. The fifth reflection is about meaning. If the universe ends in silence, does anything matter? This is a question people have wrestled with for as long as heat death has been imagined. The reflection is that meaning is not something the universe grants. It is something we create. The cosmos does not care whether stars shine or fade, but we care. We look up at the night sky and feel wonder. We study the stars and learn their secrets. We tell stories, make music, love one another. Meaning is a human act, a choice to value, to notice, to appreciate. Heat death does not erase that. If anything, it sharpens it. The sixth reflection is about acceptance. The universe is heading toward equilibrium, and there is nothing we can do to stop it. We cannot reverse entropy. We cannot prevent stars from fading. We cannot hold back the expansion of space. The laws of physics are what they are, and they do not bend to our wishes. The reflection is that acceptance is not the same as despair. It is simply recognizing the way things are. The universe will end, and that is okay. It does not need to last forever to be meaningful. It only needs to be what it is. The seventh reflection is about perspective. Thinking about heat death places our lives in context. The problems that feel overwhelming, the worries that keep us awake, the anxieties that weigh us down, all of them shrink against the backdrop of cosmic time. This is not to say that our struggles do not matter. They do. But the reflection is that perspective can be a kind of comfort. The universe is vast, and we are small. And in that smallness, there is a kind of peace. The eighth reflection is about gratitude. To exist in the luminous middle, in the age when stars still shine, is an extraordinary stroke of luck. We did not earn it. We did not choose it. We are simply here, alive, conscious, able to witness the universe and wonder about its fate. The reflection is that this is a gift, fleeting and fragile, but real. The stars will fade, yes, but they are shining now. The galaxies will vanish, yes, but they are glowing now. And we are here, now, to see them. The reflection on heat death is not about despair or nihilism. It is about seeing clearly, accepting impermanence, and finding meaning in the temporary. The universe will end in silence, but that ending does not diminish the journey. It completes it. The reflection is that the story of the cosmos, from the Big Bang to heat death, is a story of transformation. Energy spreads, structures form and dissolve, entropy rises, and in the middle of that story, for a brief time, we are here. That is what it all means. And so we come to the end of the story. The closing notes of a lullaby that began with fire and ends in silence. The universe, vast and ancient, is heading toward a future of perfect stillness. Stars will fade, galaxies will dissolve, black holes will evaporate, time itself will lose its meaning. But before that distant silence arrives, there is this moment, the luminous middle, the age of stars, the brief window when the cosmos is alive with light, and we are here to witness it. The story of heat death is not a tragedy, it is a completion. The universe is not being destroyed or punished. It is simply following the laws that have governed it since the beginning. Entropy rises, energy spreads, gradients vanish. The cosmos moves toward equilibrium, patiently, inevitably, without hurry or regret. It is the natural ending of a process that began with the Big Bang, the final chapter in a long and beautiful story. As you lie here, drifting towards sleep, let yourself picture the far future, not with fear or sadness, but with calm curiosity. Imagine the last stars fading, their light dimming to nothing. Imagine the galaxies growing dark, their spirals dissolving into scattered remnants. Imagine the black holes evaporating, releasing their last whispers of radiation into the void. Imagine the universe reaching equilibrium, a state of perfect evenness where nothing can change anymore. It is quiet there, in that future. No sound, no light, no motion. Just the thin wash of radiation spread across infinite space, uniform and still. The campfires have all gone out, the embers have cooled, the ashes have been carried away by the wind of time. The cosmos rests, not in death, but in balance. It has completed its journey. It has reached the end of the story. But that ending is so far away, it is almost unimaginable. Right now, the universe is still alive. The sun is still shining, warming your world. The stars are still burning, lighting the night sky. The galaxies are still glowing, spiraling through the darkness. This moment, this present, is the one that matters. The future may be silent, but the present is full of light. And you are part of that light. The atoms in your body were forged in stars. The energy that powers your thoughts came from the sun. You are made of the universe, a temporary pattern in the flow of entropy, a brief flame in the cosmic night. You are not separate from the story. You are woven into it, part of the same fabric that includes stars and galaxies and the slow march towards silence. As you close your eyes, let the weight of the day lift away. Let the worries and stresses dissolve like mist. The universe is patient, and so can you be. There is no rush, no urgency. The cosmos has been unfolding for nearly 14 billion years, and it will continue for trillions more. Your night can be calm. Your rest can be deep. The story will continue without you for a while, and that is okay. Breathe slowly, in and out. Feel the rhythm of your breath, the rise and fall of your chest. It is the same rhythm as the universe itself. Expansion and contraction, energy and rest. The cosmos breathes too, in its own way, expanding into the future, exhaling its energy into the void. You are part of that breath, part of the same pattern. The lullaby of the cosmos is gentle. It does not demand, it does not frighten. It simply invites you to rest, to let go, to drift. The stars are shining above you, even if you cannot see them. The galaxies are glowing across the universe, even if they are far beyond your view. The universe is vast, but it is also here, in this room, in your breath, in the quiet beating of your heart. And as you drift into sleep, let the story settle into your mind like a soft blanket. The universe began in fire, it will end in silence, and in between there is this, the luminous middle, the age of wonder, the brief time when stars shine and life can ask why. You are here, in that middle, alive and aware. That is the gift. That is the story. The lullaby continues, soft and steady. The universe does not fight its ending. It accepts it, embraces it, moves toward it with patience, and so can you. Rest is not failure, it is part of the rhythm. The stars rest when their fuel is gone. The cosmos will rest when entropy is complete. And you can rest now, knowing that you are part of the same story, the same journey. Let the darkness behind your eyelids become the darkness of space. Let the silence in the room become the silence of the far future. Let yourself float, weightless, like a particle drifting through the void. There is no weight here, no burden, only the gentle pull of gravity, the soft current of time, the quiet hum of existence. The universe sings its lullaby, and the song is this: everything fades, but everything also shines. Stars burn brightly before they dim. Galaxies glow beautifully before they dissolve. Life flourishes briefly before it rests. The ending is not separate from the journey. It is part of it, the completion, the final note. And so, as the lullaby fades, as your thoughts grow softer, as sleep draws near, remember this: the universe is vast, ancient, and heading towards silence, but right now it is alive. The stars are shining, the galaxies are glowing, and you are here, part of the luminous middle, part of the cosmic story. Rest now. The universe will continue its journey. The stars will fade, one by one, across trillions of years. Entropy will rise, silence will come. But not tonight. Tonight, there is only this: the gentle drift into sleep, the soft embrace of rest, the lullaby of the cosmos, carrying you into dreams. Good night.